Welcome to Tech Unplugged, where research and innovation goes off script and where cutting-edge technology meets everyday curiosity. My name's Dr. Daniel Mitchell, and I'm going to be leading you through the research world of symbiotic multi-robot fleets for offshore wind farms. So as we know, offshore wind farms are large structures positioned miles away from the shoreline and provide a tremendous amount of energy, enabling us pathways to net zero. However, capturing this energy leads to a significant amount of challenges which humans need to overcome within operation and maintenance. Now, the operation and maintenance phase includes anything to do with inspection, maintenance, and repair of these large offshore structures. Where the offshore environment typically is extremely hazardous due to large tides, large high gusts of wind, and dangerous areas within these offshore structures. So within this podcast episode, we're going to explore the use of robotics and artificial intelligence, where robots can do the more dangerous inspection, maintenance, and repair to make jobs a lot easier for humans that were typically deployed in those areas and allow the humans to focus on more complex tasks. So what does the state of the art look like in today's world? Currently, engineers are required to do rope access inspections alongside blades. So that's where they rappel down a wind turbine blade and do a visual inspection for any defects that are separate to the manufacturing operational state. In more up-to-date research, what we're seeing is unmanned aerial vehicles being teleoperated by a human operator, and that enables the human to stand in a safe area and the drone fly up to the blade to do these visual inspections as well, which can save a lot more time because they're much more efficient. Typically, you can find that one rope access engineer can only do one wind turbine blade, whereas a UAV can do around 3 wind turbines at a time. And then thirdly, what we're starting to see as well is the deployment of crawling robots, similar to spiders. However, the efficiency of these robots in terms of their maneuverability is not as effective as it could be for that to be cost effective offshore. With respect to substation inspection, we're starting to see a high improvement in wheeled robots, quadruped robots as well, which is the kind of 4-legged dog robot, so to speak, where within the research that's going to be presented today to you guys, we're going to see some developments from, firstly, a wheeled robot, a ClearPath Husky, with 2 UR5, Universal Robot 5, basically Model 5 manipulator arms. And then we're also going to see a Boston Dynamics Spot robot, which has a front manipulator arm on the head of the robot so that we can do some task kind of grasping and moving tasks within the operational mission envelope today. So let's take you through the first mission. So in the first robotic mission we're going to view together, we're going to see a confined space asset integrity inspection, where our symbiotic system design for resilient autonomous robots kind of started off. So here what we're seeing is the ClearPath dual-armed robot operating within an analog substation environment. On the very front of the robot, you can see a pan tilt unit, which has a non-destructive radar sensor on the front there. And within this environment, we set it up very similarly to an offshore substation, or it could be compared to a kind of nuclear use case scenario as well, where the robot is doing, you can see the pan tilt turning around there, and at the top right, we can see an asset integrity inspection mission there. Now, down the bottom right, what you're seeing is a runtime reliability ontology, which is effectively a knowledge graph or a large map of all the different interconnected systems within the robot. So within that inspection mission, we ran a a motor, and we kind of induced a motor failure on that robot, so that the robot thought it had a failure happening on the motor, and then the runtime reliability ontology was able to detect that fault and then take a reactive measure to reduce the failure rate of the robot. So within that inspection mission, we were primarily looking at safety, runtime reliability, and then self-certification for an offshore inspection scenario. Now, within this second video, what we're going to see is a scalable cyber-physical architecture, which is the conceptualization of our Symbiotic multi-robot fleet. So this is where we took the wheeled robot, we added in a dashboard for our quadruped robot, and also an unmanned aerial vehicle as well. So currently what we're seeing is the Boston Dynamics quadruped robot with the 4 legs, with a large manipulator arm on the front. We connected all these robots via a operational decision support dashboard, which you're now seeing on the screen, where we were able to task the robots, teleoperate the robots, all from a single laptop. So we were almost acting like a robot fleet manager, so to speak. Now, the kind of key objective of this autonomous inspection mission was to enable the human to stay in a safe area, allow the robots to investigate or conduct their routine inspection and maintenance within this dangerous environment. So this is where safety is completely paramount. Now, within this robot inspection mission, we pitched a scenario where each robot has an inspection task. So as we can see here, the wheeled robot is conducting a similar inspection mission to the previous mission for corrosion. However, this time we've got the inspection on the radar sensor on the actual manipulator arm. The quadruped also assists in that robotic inspection mission. And then in a similar approach, we actually conducted induced a fake failure on one of the robot manipulator arms. And we were able to successfully identify that via our runtime reliability ontology in the dashboard. Now, a key thing within this symbiotic approach is mutualism and commensalism. So mutualism is bio-inspired. Within kind of sea life is a common scenario where each robot benefits from the assistance from another. So within our inspection mission, we were able to identify a failure, which is a battery issue, and then we were able to induce an autonomous mission on the Boston Dynamics robot to be able to identify a toolbox which has got a battery, collect that battery, and then identify the Husky to transfer that battery over to the Husky. Now, the current state of the art isn't expecting our autonomous robot to be able to take apart itself and re-put itself back together. But this is about the symbiotic sharing of future sensors that are modular, and modular means that you can have a robot utilize a sensor on one type of robot, and then it can also kind of hand over that same sensor to another type of robot. So within this symbiotic multi-robot fleet, the robots were able to help each other a little bit more. We utilized machine learning to be able to detect the battery pack, transfer that battery pack to the other Husky robot, which also used machine learning via image processing to detect the Husky robot. And then we were also able to teleoperate the DJI UAV robot to be able to conduct inspections at height and in different scenarios. And I guess the other reason why we used a symbiotic multi-robot fleet of all these different types of robots is for long endurance missions, the wheeled robot has got great characteristics because it's got a large battery pack. It can conduct continuous long missions of up to potentially 4 or 5 hours. However, that robot has a limitation of getting over stairs, for example. That's where that robot could request assistance from the quadruped robot, which is a great robot because it can travel over stairs, it can carry medium payloads. However, that robot doesn't have as long a battery life and doesn't have the same payload capacity as the ClearPath Husky, which can carry up to like 90 kilos or something. But then these two ground robots, you can only zoom in from an angle you can only zoom in from certain angles, but sometimes you do need a UAV or another type of robot to be able to climb up to a certain altitude to conduct these inspection missions. And that's where our small, compact UAV was perfect in this scenario, because it had a 720p camera on it. You could get up nice and close to an environment and take a photo of any corrosion at height, and then relay that information back to our robot fleet manager to then conduct, right, this is the next routine maintenance that's needed for inspection, maintenance, repair. Now, within this research, we utilised the DARPA Subterranean Challenge as a useful benchmark to compare and contrast our findings. Within the DARPA Subterranean Challenge, it's a large American multi-robot fleet competition funded by the DARPA, and that was a long endurance inspection mission within GPS denied environments through cave structures, mines, all kind of like man-made environments, but they're to replicate environments where there's GPS denied communications, no Wi-Fi allowed, for example. Now, albeit communications wasn't something that we directly focused on within this mission or within our multi-robot fleet inspection missions that we just viewed together, it's certainly something that's extremely powerful and transferable to other sectors. So whilst offshore has got inherent communications issues, these can be resolved as they're man-made structures. We can install Wi-Fi, we can install 5G and 6G communications, but certainly within these environments, there's still going to be wireless denied environments. And that's where the learnings from DARPA, such as mesh networking, can be used to ensure that robots have the communication capability within their inspection missions. And then certainly within other sectors, we can compare it to the nuclear sector, where there's heavy, thick lead shielding, which is extremely important for the safety of personnel and equipment. But that heavy lead shielding actually blocks off any communications with the different robots, vice versa. So that's where you maybe need to overcome these things by creating mesh networks which operate line of sight, or utilise optical cables between robots to ensure that these robots can communicate effectively and send back the important data that's required for updating the humans. A challenge within robots for the nuclear sector is that robots aren't kind of invincible to radiation. So radiation can actually fry the electronics within robots, which can lead to robotic graveyards within these nuclear facilities. And that's certainly been discussed within the state of the art when we look at different British and Japanese nuclear facilities, which is very interesting with respect to resilience and reliability of these robots during their inspection missions. So to wrap up, I'd like to thank you for listening today, and some key takeaway points that from the research that we've looked at today is robots utilising symbiosis to help each other and request access and help for different types of tools or different inspection, maintenance and repair missions, and also enabling robots to be smarter and more adaptive depending on their mission scenario. So if a robot is facing a challenge, can another robot help out? Does that robot need to send a warning to a human operator at the operation decision support interface, sitting happily at their laptop? And this will in future enable engineers to be able to work on more complex engineering tasks. Thank you for listening today, and looking forward to having you in the next episode.